You want to go outside? Why don't you go out? Hey guys, welcome back. Thanks. Why don't you go out? Go on. Alrighty. Yeah, welcome back to Calc 2. Today we are going to continue where we left off last time, talking about power series. We did some integration and differentiation of power series last time. I intend to do more of that today. I'm going to recap the power series that we have learned and must remember forever and ever, amen. And then we're going to charge further forwards. So here we go. Your exams I'm working on today is the day I would hope to have them done by, and I may have them all done today. But because we did have the 4 different versions of the test, online and in person, both on the original day and on the makeup day, it just takes longer to get through them. So if you took the test somewhere other than online with me on Wednesday of last week, then it might take a little bit longer, but at least those will be done today. So this is MAC2312, section 004, which is Calc 2. Today is the 10th of November, 2021. And today we are going to do more representing functions as power series. Which is section 11.9. And we might maybe introduce Taylor's theorem, which is section 11.10. I'll get that out of the way. That's the vibe. Okay. So I'll remind you of the important results from last time. Last time we saw that 1 over 1 minus, I'm going to write it as u. I'll use the variable u in all of these because the idea is that you can then, if you memorize these, you can then get new power series by plugging into them. 1 over 1 minus u can be written as sigma n from 0 to infinity u to the n. And this fellow has IOC, -1 to 1. So he will converge if u, whatever you're plugging in here, is between -1 and 1. We also cooked up the series for the inverse tangent function. And I'll rewrite that in terms of the variable u. This we found by integrating 1 over 1 plus x squared, or 1 over 1 plus u squared, and we get sigma n from 0 to infinity, -1 to the n over 2n plus 1 times u to the 2n plus 1. And his IOC was the closed interval from -1 to 1, which was a cool example of integrating a power series and picking up endpoints. The series we integrated to get this was the series for 1 over 1 plus x squared. And his IOC, like the original one here, was open. So the kind of take-home lesson there is when you integrate a power series, the radius of convergence will never change, but you can pick up an endpoint. And similarly, when you differentiate a power series, it is possible to lose an endpoint. Today, I'm going to add to this one more power series that you must remember forever and ever, amen. And that's a power series for the natural log. No. All right. Before I do that, I think more practice differentiating series. We saw a few integrals last time. We haven't seen much in the way of derivatives of power series. So let's fart around with that a little bit. I'm going to pop open your textbook. See if they have some fun examples. If not, I'll just cook one or two up. So maybe a little bit of practice with the geometric series trick first. Number 7 looks like fun. And then number 13 over here is one that I know gives people a really hard time. So let's take a look at this. Okay. So let's find power series and the IOC for f of x equals, what was it, x to the 4 over 16 plus x squared, or other way around, x squared over x to the 4 plus 16. So the trick here is going to be using this geometric series. Like I said, the majority of the problems in 11.9, you're going to begin with this guy. Sometimes you may then integrate or differentiate like we did to find this guy. But most of the time, you're just going to do some algebra until you can massage your function into that 1 over 1 minus something form. Now here, unlike the examples from last time, my numerator is not a constant. My numerator is x squared. But what you'll see is that that's not actually going to cause us any sort of headache. The first thing is to, just like the 9 from the example we did in the start of class on Monday, we popped the 9 off the top. I'm going to pop the x squared off the top and then rewrite this as 1 over, I'll say 16 plus x to the 4, swapping the order of addition downstairs. Can anybody suggest a good next step to help push this towards looking like this? I really want interactivity here today because this is a skill we must learn. Yeah, Frank suggests we factor something. What should I factor? I've got the 1 here. I want a 1 here. I've got the 1 here. I want a 1 here. So what should I factor? 16 plus x to the 4 can be factored, but not in a nice way. And generally factoring in the sense that you factor polynomials isn't usually the thing to do here. This is already pretty close to being in this form. And if I were to factor this into 2 quadratics, which can be done, but not prettily, it would be taking me further from this form. But there is something from the denominator that I want to factor. I just don't want to factor the whole denominator as a polynomial. So maybe say, instead of saying no, just a little more clarity. Yeah, Alex's suggestion is nice. Let's factor a 16 out from that denominator. Call it force factoring. So this would be x squared times 1 over 16 times 1 plus x to the 4 over 16. So downstairs, I'm going to force factor that 16. Because I can then bring that 16 out of the big fraction and write this as x squared over 16 times 1 over 1 plus x to the 4 over 16. And now we see this fraction getting very close to the form 1 over 1 minus u. I've got 1 over 1 plus something. So what's the last little algebra maneuver here to turn this into this?
Multiply by 16 over x to the 4th.
Not quite. Yeah, Kylie's suggestion is a DM. I'm going to rewrite this plus as minus a negative. That's the only thing that's messing me up here, right? I've got 1 divided by 1 plus some shit, when what I want is 1 divided by 1 minus some shit. So My x squared over 16 out front stays. My 1 upstairs stays. And that 1 plus I can write as 1 minus negative x to the 4 over 16. That's all. So it might feel silly, but remember the goal is just to get this fraction to the form 1 over 1 minus something. I don't care what the something is. I just need 1 over 1 minus something. So this piece right here is what I will use for u. And thus, according to my geometric series formula, that fraction 1 over 1 minus this thing is sigma n from 0 to infinity, that thing, negative x to the 4 over 16 to the n. So from here to here is the big step. I've gone from not a series to a series using the geometric series trick. And this game of just kind of massaging this thing algebra-wise until it looks like 1 divided by 1 minus something is the main trick in 11.9. But I'm still not happy with this answer. This doesn't look like a power series. I want sigma cn x to the n, or something like that. As close to that as I can. I want to be able to tell what the coefficients are and what the center is. So from here, we need to use the algebra rules for the sigma operator to just clean things up. I'll leave the x squared over 16 out for now. And just work inside the sigma. So this is x squared over 16 times sigma n from 0 to infinity of negative x to the 4 over 16 all to the n. That's negative 1 to the n over 16 to the n times x to the 4 all to the n. Just basically taking this thing, which is a bunch of stuff multiplied and divided, all raised to the n, and giving that nth power to each of the pieces. So the negative is the negative 1 to the n. The 16 here is the 16 to the n. And x to the 4 all to the n is x to the 4 all to the n. Still not quite looking like a power series, though. First, I've got this shit outside. Second, I've got x to the 4 to the n instead of like x to some power. So my next step is to rewrite this as x to the 4n. All right, it's just one of those rules, algebra rules, right? A to the b, all to the c is a to the b times c. So x to the 4 all to the n is x to the 4n. The only thing I've changed in this step. Now we're ready to finish the job. I've got a 16 downstairs here. I'm going to move this whole chunk inside the series. I'll do it in separate steps because we're still just kind of learning this. But in the future, I'll do this as a single step. So this is 1 over 16 times negative 1 to the n over 16 to the n times x squared times x to the 4n. So I'm moving the x squared over 16 inside. The over 16, that's a 1/16. I'm going to put that right here because that's a constant. It doesn't have any x's. And the x squared, I'm going to put next to the x to the 4n because it's got some x's in it. And I intend to combine this with this and this with this. The next line will be our final answer. When I combine those, I get sigma n from 0 to infinity. -1 to the n over 16 to the 1 times 16 to the n is 16 to the n plus 1. And x to the 2 times x to the 4n is x to the 4n plus 2. Again, just basic algebra rules. But it's done within the sigma operator. This is your final answer. This is a power series centered at 0 for this function.
Can we simplify the 4n plus 2 to 2n plus 1?
Well, you could write it as x to the 2 times 2n plus 1, but I wouldn't. Like, you could factor a 2 here, but then that's not going to go away. So I would just leave it like that. Okay. We do also want the interval of convergence, and there's multiple ways to get this. If I handed you this out of nowhere and said, find the IOC, probably the natural thing to do would be to run the ratio test. But I know where this came from. This came from the geometric series trick. So this guy will converge since this comes from geometric series. It will converge if and only if the absolute value of u is strictly less than 1. Right? This is a geometric series where my common ratio was u. So that means the absolute value of -x to the 4 over 16 is less than 1. I'm going to need some more space here. That is the same thing as, I'll continue it over here. That is the same thing as absolute value of x to the 4 over 16 is less than 1, right? The negative inside the absolute value just goes away. Then you can split up the absolute value as the absolute value of the top over the absolute value of the bottom. Absolute value of 16 is 16. Multiply both sides by 16 and bring the power out of the absolute value. You get absolute x to the 4 is less than 16. Taking fourth roots, that's the absolute value of x is less than 2, i.e. -2 is strictly less than x is strictly less than 2. So the IOC is the open interval from -2 to 2. And we don't need to check endpoints. Don't need to test the endpoints because this is a geometric series. Right? If I had done some calculus, if I integrated this, then I would need to test the endpoints because integrating that power series, I might pick one of them up. But as is, it's just a straight up geometric series. This might not look like a geometric series because we've rewritten it in this nice form, but look at it here. This guy is clearly geometric, right? It's just some shit all raised to the n inside your sigma. That is by definition a geometric series. So he will converge exactly when the shit inside here has an absolute value smaller than 1. And that is true exactly when x is coming from the open interval -2 to 2. If x is equal to 2 or -2, the series will diverge because it would be a geometric series with common ratio 1 or -1.
Why does the absolute value drop for 16 but not for x?
Because 16 is just a number, it's a positive number, and the absolute value of 16 is 16. But x is a variable, and x could be positive or negative.
But isn't it, if you put any number into x, even if it's negative, because it's the fourth power, then it would end up being positive?
It's true that x to the fourth will end up being positive, yep. But remember, the absolute value commutes with powers. So the absolute value of x to the 4 is the same as the absolute value of x all to the 4. And this quantity right here is not guaranteed positive. So what we're trying to do, remember, is solve this inequality. I want to find all the numbers x that would make this inequality true. And we need to be mindful that there are negative numbers for x that would make this inequality true. For example, plug in -1. If you plug in -1 for x here, you would get -1 to the 4, which you're correct is +1. So this would be +1/16, and that is less than 1. But this way of managing the algebra is the easiest way to arrive at this solution. So yes, you're correct that if we were to plug any number in here for x, this would become positive. This would become positive. And it is true algebraically that the absolute value of x to the 4 is the same as x to the 4 itself. But my goal is to arrive at an inequality that looks like this. The absolute value of x is less than some constant. So it's with that in mind that I don't toss away the absolute values on the variable. And this is what we always do. So I'm glad that you asked that. But what I'm trying to do here is outline a procedure that will always yield the correct result. And the procedure that always yields the correct result is keeping the absolute value on the variable and then dismissing it on any constants that can be pulled out. Another way of saying this is if we drop the absolute values here, you would just get x to the 4 is less than 16. And I think a lot of people would have a harder time solving that inequality than solving this inequality. It's true that the solution to the inequality, x to the 4 is less than 16, is the same.
Yeah, I mean, you just do the fourth root to each side and you'd get 2.
Well, that's not true. So that's the thing. So when I say most people have an easier time solving this inequality than this inequality, that's precisely what I mean. The way you solve, I'm glad we're doing this. You don't need to write this down, but think along with me for a second. Anybody remember how to solve inequalities like this? Taking fourth roots doesn't work. Right? You cannot take roots through inequalities unless you know everything is positive. And we do not know that x here is positive. So the way you would solve this is something we do in pre-calculus, but then everybody forgets it. You pull everything to one side, you factor. This can factor as a difference of squares first. And then the x squared minus 4 factors further as x minus 2x plus 2.
Yeah.
And then you write down your cut points, which are the points that the x values, which would make that equal to 0, which are -2 and +2. And then you test a point in each region, use multiplicities. If you test x equals 0, this will be positive. This would be -2 times +2 times +4. This would be negative. And these would be positive. So the solution to x to the 4 minus 16 is the open interval -2 to 2. If you try to take fourth roots here, then if you take the positive fourth root, you'll get x is less than 2. If you take the negative fourth root, you'll get x is less than -2. And that wouldn't make sense, right? This is not the same as saying x is less than 2 or x is less than -2. That sort of stuff doesn't work. And that's sort of the take home of this lesson in pre-calculus. So for that reason, right, for exactly that reason, I recommend handling it this way, because getting down to an absolute value inequality like this is a lot easier than managing a gnarly polynomial inequality like this. And also, if the power wasn't even, then trying to ditch the absolute values just wouldn't be kosher, right? Because an odd power could output a negative number. So this procedure is nice, clean, and quick, and it always works. You'll never end up in a situation where you write down something that is untrue or struggle to get the interval you need. And that's why I do it this way.
Thank you.
Of course, of course. Other questions, comments on this? This is kind of the meat and potatoes of section 11.9. So I'd like to take whatever time we need here to feel comfortable. Yeah, so there was a question here about how I took the fourth root at this stage. The kind of rules for inequalities are a little bit sneaky. Once we arrive here, I can justify taking the fourth root because I know that this and this are positive. So I'm looking at an inequality between strictly positive quantities, which guarantees that when I take that fourth root, I don't need to worry about the -2 that would normally come, right? When I take an even root, usually you get plus and minus, but the absolute value of x could never be smaller than -2. So when you're dealing with inequalities of strictly positive quantities, you can take roots on both sides. The place you get into trouble is if you were to rewrite this as just x to the 4 is less than 16 and try to take roots. So because I've left the absolute value here, I am allowed to just take the fourth root. That's kind of the sneaky move. The good news is with a little bit of practice, this will feel very natural. And unlike rewriting it without the absolute values, you won't end up in a situation where you say something false. And just for shits and giggles, what's the center of this series? Where is this power series centered?
Zero.
Very good, right? Because this is x minus 0 to the 4n plus 2. Also, you could see it from here, right? This interval is symmetric about 0. So the IOC is always symmetric about the center. What's the radius of convergence?
2.
2. Very good, right? The distance from the center to the endpoints. All right. That out of the way, let's look at some calculus operations on power series. We did some of this before. I think I'd like to start with number 13 here, where we're differentiating power series. So we want, the problem says, use differentiation to find a power series for 1 over 1 plus x all squared. The way I would phrase this on a test is just find a power series for f of x equals 1 over parentheses 1 plus x all squared. And the suggestion from the book there is to use differentiation. So you have to ask, what am I going to differentiate? Am I going to differentiate this thing? Or am I going to differentiate something else to get this thing? The correct answer is the latter. I want to differentiate something to get this. Ideally, I would differentiate something whose power series I know to get this. So what I would do is I'm going to ask myself the question, what function has derivative 1 over 1 plus x squared, which is the same as 1 plus x to the negative 2. If I can identify that function and find a power series for it, then I will differentiate that to get this. The arctan is not a bad guess, but remember the arctan is 1 over 1 plus x squared. And this is 1 over 1 plus x parentheses all squared. So it's not the same thing. This looks like, if not for the parentheses, this would be the derivative of arctan. But also we want to go the other way. We want to know what function do I differentiate to get this? One option is to integrate this. If you integrate this function, you will find something whose derivative is this function. But I want to strongly caution you against that because it's very easy to forget what direction you're trying to walk in the derivative chain. Here's how I think of it. Imagine the 1 isn't here. This would just be x to the negative 2. Who has a derivative that looks like x to the negative 2? Think power rule. Well, the derivative of x to the negative 1 is negative 1 x to the negative 2. So we think maybe 1 plus x to the negative 1 has that derivative. The answer is going to be not quite, but very, very close. So let's check. If you calculate d dx of 1 plus x to the negative 1, you get negative 1 times 1 plus x to the negative 2 times 1 by the chain rule, which is damn close to what I want. This is negative 1 over 1 plus x all squared. So what does this mean? Well, if I multiply both sides by negative 1, I discover that negative 1 times d dx of 1 plus x to the negative 1 would be 1 over 1 plus x squared, which is the function I want. Is it easy or hard to find a power series for the function 1 plus x to the negative 1?
Can I ask how you got the negative 1 and the 1 on the side?
Here?
Yes.
So the negative 1 comes from the power rule, right? I'm differentiating this thing. So I bring down the power and subtract 1 from the power.
1, okay.
Gives me negative 1, that thing to the negative 2. And then by the chain rule, I have to multiply by the derivative of the inside. The derivative of 1 plus x is just 1.
All right, thank you.
Yeah, no problem. So here's what I've discovered. My function, f of x, the thing I want a power series for, is equal to negative 1 times d dx of 1 plus x to the negative 1. I'll tell you that this kind of thinking is somewhat similar to the kind of thinking you will use in differential equations. So think of this as training for the next course. So the thing I want a power series for is negative 1 times the derivative of this thing. So if I can find a power series for this thing, I can then differentiate that power series and then multiply by negative 1, and Bob's your uncle. You got the function you want. That is -1 d dx 1 over 1 plus x. All right, 1 plus x to the -1 is 1 divided by 1 plus x. So I'm going to use my geometric series trick here to get a series for 1 over 1 plus x. Then I will differentiate that series. Then I will multiply by -1. I'll do this all very carefully. So that is -1 d dx 1 over 1 minus -x. Now I've got 1 over 1 minus something. That's the form to which I can apply my geometric series trick. This is -1 d dx sigma n from 0 to infinity -x to the n. And before I can differentiate that power series, I need to simplify it a little bit. I don't know how to differentiate stuff like this. I need to get rid of the negative inside. Technically, you could do it with the chain rule, but my advice is to always clean up a power series before you integrate or differentiate it. Always. By clean it up, I mean write it in that standard form for a power series. So this is -1 d dx sigma n from 0 to infinity, -1 to the n, x to the n. A common mistake when differentiating or integrating stuff like this is to integrate or differentiate with respect to n. But we're not. This is d dx. We're integrating or differentiating, in this case, differentiating with respect to the variable x. So all the n stuff is constant, it just comes along for the ride. The only place I have an x here is x to the n, whose derivative by the power rule is n times x to the n minus 1. And I've left the bounds off my series for a reason. Does anybody remember what happens to the bounds for this series when I differentiate?
It increases by 1, the starting point?
Yeah, the starting index jumps by 1, but only if the original series has a constant term. So what I should do before I write down those bounds is check to see if the series has a constant term. In other words, I should write out the first few terms of that series. When n is 0, we get 1. When n is 1, we get minus x. When n is 2, we get plus x squared. When n is 3, we get minus x cubed, and so on. So that series does have a constant term. Since our series does have a constant term, we bump the starting index by 1 when differentiating. Remember the idea behind this is the n equals 0 term, this is the n equals 1 term, this is the n equals 2 term, this is the n equals 3 term. The n equals 0 term, because it's a constant, will differentiate to 0. He will go away when we take the derivative. So there is no longer an n equals 0 term. The first term in the derivative of this would be the derivative of this negative x piece here. The n equals 0 term vanishes. So this becomes sigma n from 1 to infinity. And that's something you want to watch out for. Julian also makes a comment that we can lose endpoints. That's correct. So what is the interval of convergence for the series we differentiated? We should be mindful of that as well. This would come from solving the inequality. Absolute value of u is less than 1. U here was negative x, so this is absolute negative x is less than 1, which is the same as saying absolute x is less than 1, which means negative 1 is less than x is less than 1. So the IOC of the series before we differentiate is the open interval from negative 1 to 1. So while it's true that when you differentiate a power series, you can lose endpoints. We don't always lose endpoints, but you can lose endpoints. Do I need to be concerned about that here? Does this original IOC contain either of its endpoints?
No.
No, it doesn't, right? That's what the parentheses mean. It means that this is everything strictly between negative 1 and 1. So if this was a closed interval, or maybe just closed on the right, or just closed on the left, then I would need to, at the end, check and see whether this new series lost an endpoint. But since the original series IOC is open, containing neither endpoints, losing an endpoint can't happen. It already doesn't have either of them in it. But you're correct, Julian, that it's possible we lose endpoints. All right, we're very, very close to being done. The only thing we need to do now is to move that negative 1 inside. Negative 1 times negative 1 to the n is negative 1 to the n plus 1. So the power series we're looking for is sigma n from 1 to infinity, negative 1 to the n plus 1, n x to the n minus 1. And the IOC, we can reason without doing any more work, must be the same as the original IOC. The radius of convergence will never change. The only thing that can happen when you integrate or differentiate is picking up or losing endpoints. Remember, when you differentiate, you can lose endpoints. When you integrate, you can pick them up. But since the series I began with contains neither endpoint, the IOC here is still the same. The open interval from negative 1 to 1. And while you could take the time to check this using the ratio test, you really don't want to, because, for example, on an exam, you will run out of time. So these theorems are theorems that you should know, because they are big, big time savers, right? I do not want to run the ratio test and then test endpoints all over again. We just know that I started with the IOC negative 1 to 1. So the endpoints for my new IOC have to stay negative 1 and 1. Since the original IOC was open and I took a derivative, the only thing that could happen is I lose an endpoint if I happen to have them. But since I do not have either endpoint, my resulting IOC has to be the same as the original. So that's that. This is the power series for 1 over 1 plus x all squared. I know it looks intimidating. I get that. And this, again, is why this class has the reputation it does. But I also promise you that it is extremely logical. And as long as you practice, really practice, you will get good at this. The other thing I promise you is if you're going into any hard science, physics, chemistry, engineering, any of those, this is the most important part of any math class you're going to take, power series. If you're going to do any sort of numerical analysis, God forbid you want to be a mathematician, power series will be hugely important, but also engineering, statistics, probability, any place where you're working with functions as a regular part of your life, physics, chemistry, all of that. Power series are the game. Fourier series also, but Fourier series outside the scope of this class. All right. Here's the whole procedure. Questions on this guy? There are more parts to question 13, and the WebAssign analog of this question I did put in your homework. So I'm going to go ahead and show you parts B, at least parts B and C. We can do these quite quickly. So what we're going to do is use the fact that 1 over parentheses 1 plus x all squared is equal to sigma n from 1 to infinity, negative 1 to the n plus 1, and x to the n minus 1, to find power series for two other functions, for 1 over 1 plus x cubed and x squared over 1 plus x cubed. So I've just written down the result from part A, and we want to use that to find series for these guys. How do you think we're going to get the series for 1 over 1 plus x all cubed from the series for 1 over 1 plus x all squared? Any guess on the relationship between 1 over 1 plus x squared and 1 over 1 plus x cubed? Think power rule. Well, this is almost certainly very close to the derivative of this. The derivative of 1 over 1 plus x all squared, again, I'll do this with the chain rule, that's 1 plus x to the negative 2 that we're differentiating, is negative 2 times 1 plus x to the negative 3, applying the power rule. And then by the chain rule, we multiply by the derivative of the inside, which is just 1. So that's negative 2 over 1 plus x all cubed. So this thing that I want for part B is almost the derivative of the thing I found in part A. This means that negative 1/2 ddx of 1 over 1 plus x all squared is equal to the thing I want here. Right, dividing both sides by negative 2 or multiplying both sides by negative 1/2. And then this thing is the thing I just found a power series for. Therefore, 1 over 1 plus x cubed, just is negative 1/2 ddx 1 over 1 plus x all squared. And that is -1/2 d dx of this power series. Sigma n equals 1 to infinity, -1 to the n plus 1, and x to the n minus 1. So now I will differentiate this series. I get -1/2 sigma. I'm going to leave the bounds off for now. -1 to the n plus 1. I'm differentiating with respect to x. So the n stuff is all constant, doesn't change. The derivative of x to the n minus 1 is n minus 1 x to the n minus 2. Does this series have a constant term? Well, when you plug in n equals 1 here, you get -1 x to the 0. X to the 0 is a constant. So yes, we will bump this starting index again. There's the power series for 1 over 1 plus x cubed. You can bring the 1/2 in if you want. It doesn't really make a difference here because it doesn't have any x's or n's or anything like that that could make a difference inside. But if you want to be picky about it, if you want sigma of something for your answer, it's sigma n from 2 to infinity. The negative, I could get involved with this -1 to the n plus 1. I could call that -1 to the n plus 2 over 2 from the 1/2. Then n minus 1 x to the n minus 2.
So you said for that last step, we don't need to bring in the -1 over 2, right?
If you left it like this on a test, I'll be perfectly happy. You get here, I'm celebrating, setting off fireworks, all that good shit. All right, so this is a satisfactory answer, either of these, satisfactory answer for the first part here. Then part C asks for this guy. The relationship here is not so bad. I don't need to do any more calculus. X squared over 1 plus x all cubed is x squared times 1 over 1 plus x all cubed. And 1 over 1 plus x all cubed is the series I just found. So this would be x squared sigma n from 2 to infinity, -1 to the n plus 2 over 2, and n minus 1 x to the n minus 2. And when I bring that x squared inside, x squared times x to the n minus 2 is just x to the n. So that's all I'm doing. I'm just bringing this x squared in. When he hits this, it becomes this. Alrighty. So probably how you're feeling right now is a function of how much of the homework you've done. I'm not going to pretend like this comes naturally to anybody. It doesn't. It just doesn't. But if you spend enough time practicing, it will start to feel comfortable. I promise you that. I'm sure it's not what you want to hear, but there is a little bit more that we can do with each of these. At least each of these can be modified slightly to make them look prettier. And in some instances, well, I wouldn't require you to do it on a test in Calc 2. If this were differential equations, I would require you to. And I believe at least one question in WebAssign is going to ask you to do something called an index shift. So the answers we've provided here, I'm going to zoom out, are in some senses unappealing. Damn it, other way. Are in some senses unappealing. This series starts at 1, and both of these series start at 2. We like our power series to start at 0 wherever possible. The trick to doing such a thing, to taking a series that starts at 1 or 2 and changing it to start at 0, is the series version of a U-sub. It's called an index shift. So what I'm going to do now is show you how to index shift these series to all start at 0. Again, this is not required on our exams. If you give me these answers, I will jump up and down, clap for joy, set off some fireworks, all that. But it is an important skill, and it will be necessary in future classes.
For that last part, if we kept the x squared outside, would that not be considered?
Yeah, I do really want the x squared to come in. Yeah, I do want this to at least be in the form Cn x to some power.
Okay.
So index shifting. It's like U sub for series. There's a few ways to do this. One of them is to just take the series and write it out, and then ask yourself, can I think of a way to rewrite this starting at n equals 0? So let me take the example we had from part A. This was sigma n from 1 to infinity, -1 to the n plus 1 times nx to the n minus 1. I think since I'm saying that this is U sub for series, let me show you that attack first. Now, for indices of summation, we usually use letters like L, M, N, K, stuff like that, middle alphabet stuff. So here what I'm going to do is I'm going to make the substitution K equals N minus 1. Kind of with the meta goal, not of making this a 0, but making the power of x n, or k, just some variable. This means that k plus 1 is equal to n. That's a useful thing to write down. When n is equal to 1, think about how you change bounds in a U sub. You just plug the old bounds into your substitution. So when n is equal to 1 here, what is k? K would be 1 minus 1, which is 0. So my new series will start at 0. When n is equal to infinity, k would be equal to infinity minus 1, which is definitely still infinity. So I can rewrite this as sigma k from 0 to infinity. -1 to the n plus 1. Well, what is that? If k is n minus 1, then n is k plus 1. So n plus 1 would be k plus 2. N would be k plus 1. And x to the n minus 1 would be x to the k. So you see now here I have a power series starting at 0. And I've also got the nice fact that my variable is just raised to the k. The part that bothers people is when you then just replace all these k's by n's, which you can do because it's a dummy variable. It's an index. So you could then just say this is the same as sigma n from 0 to infinity, -1 to the n plus 2, n plus 1, x to the n.
Can you explain how you got the -1 k plus 2?
Yeah, so I had -1 to the n plus 1, And for this n, I'm just writing k plus 1. So n plus 1, this means that n plus 1 is k plus 1 plus 1, which is k plus 2.
Okay, thank you.
Yeah, no problem. The idea is I could relabel this series with like anything. I could call this sigma j from 1 to infinity, negative 1 to the j plus 1, j x to the j minus 1. The label name doesn't matter. This is the index shift. And then going from here to here, the symbol you use doesn't matter. So you can go back to calling it n if you want, or you could leave it as k. When I do this stuff, honestly, I leave it as k. It just feels better to me because I'm not overloading the variable n to mean multiple different things. Prashant asks a good question. Do we sub for whatever the power of x is? Usually when you're doing an index shift, yes. It depends on what your goal is, though. So most of the time when we're index shifting, the goal is explicitly to make this x to the k or x to the n to get rid of any other weirdness in here. That's usually the reason we do it. But sometimes we do it just to change the starting index from 1 back to 0. So you can think of it either way. If your goal is to have just x to your index, then you will sub for whatever the power of x is. If your goal is to move this index back down to 0, then you would sub for whatever does that, right? So if this one starts at 0, I would want to subtract 1 from that starting index to get my new starting index. Let's look at the other guy. We had 1 over 1 plus x all cubed is sigma n from 2 to infinity, negative 1 to the n plus 2 over 2 n minus 1 x to the n minus 2. If I make the sub or index shift k equals n minus 2, this will also do both. That will make this an x to the k. And also because 2 minus 2 is 0, that will change my starting index back to 0. This would mean k plus 2 is equal to n. When n is equal to 2, k is equal to 0. When n is equal to infinity, k is equal to infinity. So this would be sigma k from 0 to infinity, negative 1 to the, let's see, what is n plus 2? Well, if n is k plus 2, this is going to be k plus 4 over 2. N is k plus 2, so this is k plus 2. N minus 1 is k plus 2 minus 1 is k plus 1. And x to the n minus 2 is x to the k. And if you want, you can rewrite this as sigma n from 0 to infinity, negative 1 to the n plus 4 over 2, n plus 2, n plus 1, x to the n. It's probably not that bad. The last one, you'll see I already had an x to the n there. But if my goal is to shift the index, the starting index back down from 2 to 0, what did we have? We had negative 1 to the n plus 2 over 2, n minus 1, x to the n. So if my goal was to make this series start at 0, even though I have an x to the n here, I would still make the same substitution, right? The k equals n minus 2 substitution is what changes this from a 2 to a 0. It's going to mess up the power of x, which is unfortunate. But, you got to pick one. Have your cake or eat it. So if I make the sub k equals n minus 2, again, k plus 2 is equal to n. Pretty much everything here is going to be the same. When n is 2, k is 0. when n is infinity, k is infinity, and we would get sigma k from 0 to infinity, -1 to the k plus 4 over 2 k plus 2 times k plus 1 times x to the k plus 2. It can't be helped here. It can't be helped. Either you're going to start at 0 or you're going to have x to the k. You can't get both. But I do believe that the analog of this problem on WebAssign gives you sigma n from 0 to infinity. You don't get to type that. So you have to know how to shift it down in order to get the answer that they're looking for. Which here, if we go back to n's now, would be like -1 to the n plus 4 over 2 n plus 2 times n plus 1 times x to the n plus 2. Okay, what else? There is a little bit more that can be done to clean each of these up. These powers of -1, you notice that in all the series work we've done, sequence work 2, you've never seen -1 to the n plus 4 or -1 to the n plus 2. And there's a reason for that. It's because both of those are the same as -1 to the n. Let me tuck off to the side over here a little note. -1 to the n plus 2 is -1 to the n times -1 to the 2. And since -1 squared is 1, this is really the same as -1 to the n. And the same is true for -1 to the n plus 4. So if I wanted to, for example, in this last guy, I could write sigma n from 0 to infinity, -1 just to the n over 2, and then n plus 2, n plus 1, x to the n plus 2. And I can do the same shit in the other series as well. This would be sigma n from 0 to infinity, -1 to the n over 2, n plus 2, n plus 1, x to the n. And the top guy would be sigma n from 0 to infinity, -1 to the n, n plus 1, x to the n. So sort of the nicest possible way of writing the answers for those are these boxed statements here. And I want to reiterate on the test, you don't need to do any index shifting. I don't care, right? Give me the series starting at 2 or 3. I don't give a fuck. Leave the power of x as x to the n minus 2. I don't give a fuck. Just give me the correct power series. However you write it, give me the correct power series. I'll be happy. I promised to show you one more power series today that you need to remember forever and ever on. And none of these are those. Of course, these are just examples, exercises, homework problem type things. But there is one more. There is one more power series I really do need you to commit to memory, and that's the power series for the natural log function. In the next section, which is 11.10, we will discover a few more: sine, cosine, e to the x, stuff like that. But the last thing we're going to do today is find the power series for f of x equals the natural log of 1 plus x. The natural log of x is undefined at 0, and I'd like to center my series at 0, so I have to use ln 1 plus x or 1 minus x or something like that. The game here is that the natural log of Again here is that the natural log of 1 plus x, we know to be the integral of 1 over 1 plus x dx. And I can write 1 over 1 plus x as, we've done this a few times now, sigma n from 0 to infinity, negative 1 to the n x to the n dx. 1 over 1 plus x is 1 over 1 minus negative x. Integrating, I get a plus c, which I write in front of the series to make it clear that it's not inside the sigma. No funny business with the index when you integrate a series, thank goodness. The n stuff is all constant, so negative 1 to the n, just chilling. When I integrate x to the n, I get 1 over n plus 1, x to the n plus 1. So the natural log of 1 plus x must have this power series representation for some number c. And like we did with the arctan problem, we now need to solve for c by plugging x equals 0. You get the natural log of 1 plus 0 is equal to c plus, and then again, we always write out the terms of the series here before we plug in. The first term of the series is x, right, x over 1, and then you have minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus, and so on, evaluated at x equals 0. Since there is no constant term in here, every piece of this really is 0. So you get the natural log of 1 is equal to c plus 0. Since the natural log of 1 is 0, you get 0 equals c plus 0. So c is indeed 0, which means that the power series for the natural log of 1 plus x is sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. The interval of convergence for the series we started with, this guy, is the open interval from negative 1 to 1. But I integrated, so I could pick up an endpoint. If you plug positive 1 in for x here, then this piece just becomes 1, and you get the alternating harmonic series, which converges. So the IOC for this series includes positive 1. If you plug in negative 1 for x here, you get negative 1 to the n times negative 1 to the n plus 1 is negative 1 to the 2n plus 1. The series no longer alternates. So the IOC for the resulting series is left open, right closed. And this is that last power series that you need to remember forever and ever, amen, from section 11.9. You can write it with U's if you like, because sometimes we will plug stuff in for you. This is how I knew that the alternating harmonic series converges to the natural log of 2, by the way. You can remember it either way. The very last thing I want to say here is that those 3 series now, the geometric series, the arctan series, and the natural log series, should not be thought of as endpoints, like should not be thought of as answers. They should be thought of as starting points as we move forwards. So one last quick example before I let you go. I could tell you to find a series for the natural log of 1 plus x cubed. And the smart move here is not to start from scratch. I would say, we know that the natural log of 1 plus u is sigma n from 0 to infinity, negative 1 to the n over n plus 1 times u to the n plus 1. So the natural log of 1 plus x cubed, I would find by substituting or plugging in x cubed for u. Has to be sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x cubed to the n plus 1, which can be cleaned up as sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x to the 3n plus 3. This is also useful for doing integrals, stuff like that. So there are a few problems towards the end of section 11.9 that ask you to do something like integrate something like the inverse tangent of x over x dx. And again, here we use one of those known series, the arctan series, as our starting point. We know that the inverse tangent of x is sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times x to the 2n plus 1. So the integral of arctan x over x dx is the integral of 1 over x times arctan x dx. You rewrite the inside as a series. The 1 over x piece is 1 over x. The arctan piece is sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times x to the 2n plus 1. And then this 1 over x, I can bring into the series. So I have integral sigma n from 0 to infinity, negative 1 to the n over 2n plus 1. 1 over x times x to the 2n plus 1 is x to the 2n. And then you do this integral using the result from last time. How do you integrate power series? You just integrate the x term. So this would be c plus sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times. I increase this power by 1 and divide by the new power. So I get x to the 2n plus 1 over 2n plus 1. And here there's no, you don't need to solve for c. They asked you to do an indefinite integral. Those always have a plus c in them. So this is it, you're done. These last two problems are kind of the most important in the sense that they illustrate the utility of power series. And we will do many, many more of these as we move into section 11.10. I think I gave you one or two like this, so I just wanted to shove in an example or two here where you can see what we're doing. That's it from me for today, guys. Please, please be working hard on this stuff, all right? I know that it looks scary at first, but I promise you it feels really good to nail it. It feels really good to go to the library and fill up a whiteboard with all of this crazy power series stuff. And there's just nothing in the world that is more useful or powerful as far as basic mathematics is concerned. If you want help with any of this, you can always come by my office hours, send me an email, Canvas message, Discord. You all know the drill at this point. Next time, we're going to talk about Taylor's formula, which is a kind of very general formula for getting power series for functions when you can't do anything that we've done in 11.9, like e to the x or sine x or cos x. No using geometric series tricks for those. You've got to do something else. And the Taylor formula is sort of the best tool we have for it. So please practice hard, work hard on this stuff between now and our next meeting on Friday. On Friday, I will introduce Taylor's theorem, and I'll probably do a few more problems like this to also sort of get you comfy. But you need to be working hard. If you're not working hard here, you're gonna fall way behind really fast. So please work hard. If you need help, ask for help. I'm here, and I'll see you all on Friday.